shipping Rust to Python, TypeScript, and Ruby users. Probably a terrible idea, and that's what we're going to talk about. AKA spreading the glory of Ferris, or gospel. Please ask questions. I'm going to hit a lot of different things. There are going to be topics that you don't know about, that possibly I don't know about, and I would like to answer as many questions as possible so I leave as few people behind as possible. Doing this, you probably shouldn't do this, but sometimes you do have good reasons. And if you do have these reasons, you will need to make some decisions. And I'm going to walk you through all three of these stages. Why you shouldn't do this, why you might want to actually do this, and then like what I'm going to spend the most of my time on, kind of the questions that you want to think about as you're going to do this. So Jack talked a lot about like the low-level details of like the very lowest layers that you can be involved in here, right? C underpins all of like Python, Node runtimes, Ruby runtimes, and is like kind of like the lingua franca of like low-level computer stuff these days. All of my stuff is going to be like 5 layers zoomed out. And I'll zoom in a little more in some of these slides, but not too much. So the first part, reasons why you don't want to do this. There are pitfalls. You're going to run into a lot of things. Jack very sensibly did not try to do very much live demoing, because the moment you try to do live demos with any of this, or if you try to do like anything like involved, you very rapidly just run into like screens full of compiler errors. I think this one was specifically because I forgot to copy paste one line of code into a build.rs file, and I can reproduce that very easily because I remember exactly which line I had to add back in. And like, we kind of know what compilers are. Like, we've run cargo build. Linkers are a thing that like you see when you run Rust, when like a Rust error happens, like you decide to like cross compile your Rust code for some platform, and then it yells at you about ring, and you're like, what's a linker? Now I have to like learn what a linker is, and it's not particularly pleasant. Your release process gets way more complicated. This was our release process like I want to say a month ago. There's now like 3 more boxes on this graph right now as of like 3 days ago, and you can kind of see the pain that one of my coworkers went through. Try package this, set up npm, blah, 2, fix packaging paths, fix Windows thing, add more targets, FML, retry, fix version, fix packaging, more tries. It's a lot of pain. Not shown here is that each of these runs is like 15 minutes, anywhere between like 5 and 15 minutes. And like the iteration method is pressing git push, cracking open the GitHub UI, and just watching your workflows fail and be sad when they fail. You will also learn things you're very much happier not knowing. When I went and did the Ruby stuff for us, Ruby has 1, 2, 3, 4, 5, 6, 7, 8 different ways of passing arguments into functions. Rust has 1, thank God. And fun fact, if you want to write interrupt code between Rust and Ruby, you kind of need to be aware of like what each of these things are. So like kind of like linkers are black magic. Every one of these types is its own form of black magic, which is like, sometimes we like logic puzzles. Other times we would like them to not be in the critical path of our work. So that's all the reasons why you don't want to do this. Why you would want to do this, to be a little bit more serious. If you want to support languages, if you want to support your users in multiple different languages, right? People use languages that they've learned. People use languages that they're productive in. And people use languages because sometimes the ecosystem in one language is a lot more well-suited to their purpose than the ecosystem in a different language, or just because like they find it easier to hire Python developers or TypeScript developers than Rust developers, right? Like it's easier to hire them. There's a lot more people who learn these languages like coming straight from like no technical background. And so like if your users are in a lot of these communities, then you kind of want to go to where your users are. In our case, so I work at Boundary ML. We build BAML. We build a new DSL for calling LLMs and providing guarantees around what LLMs give you, the shape of the information you get back. all of the people that are building LLM-powered applications write their code in Python. They write their code in TypeScript. They write their code in Golang and Rust, occasionally in Rust, Ruby, all sorts of different things. And so the reason that we did this is we said, okay, we want to be able to build our software so that people in all these different ecosystems can use our stack. But we also want to retain our sanity while doing so. And Go is actually in the works right now. But kind of like what I'm showing you right here, right, is this is BAML code up here, and down there, that's Python code. You have autocomplete in Python out of our BAML code. And the reason we're able to do that is because of Rust. And we can do exactly the same thing across TypeScript. We can't really do this in Ruby because autocomplete is a lie in Ruby. And for some reason, they haven't fixed this in 20 years, and I don't really ask questions. So that's one side, so polyglot use cases. The other reason is that Rust lets us move fast and not break things. To give you some more, to make this very concrete, so we're seed stage. We have 6 people total. Our 2 co-founders wrote their first Rust code in October 2023. So we're talking 18 months ago. I joined February of last year. I started writing Rust in December of 2023. So I've got less than that under my belt. We're now a team of 6, and our default to this day is to not do code review. And we're past the 100,000 lines of Rust. I think most of us who do any kind of things at a team with many people very quickly realize hey, if I want to know what you're working on today or tomorrow or in 2 weeks, we need to do code review so we can know what's going on. Because of the things that we can just encode in our source code by virtue of Rust compiler guarantees, we can actually do this. And we don't really have bugs around the shape of our data. And it's worked for us. So now that I've kind of given you a sense of the whys, the why nots and the whys, let's take a look at some code. So you can go to that link to check it out. I will flip over to an IDE to actually show you what's going on here. So this is let me magnify this a little bit more. This is some Python code, right? We've got main.py, we've got hello from my Python app, and I will flip over to a terminal, and oh god, I forgot my up arrow does that. I'm gonna do this very involved command. And so Jack showed you the CC build command and the magic that was in his build.rs. This is the manual version of doing that. And oh my goodness, what is okay? Oh, because I'm in the wrong direction. Okay, I'm just gonna do, this is the hot reload commands that I have. So we have hello from my Python app. What I'm now gonna do is uncomment this line, which is calling into a Rust crate and telling it, hey, I want you to run a web server on port 3000. So now this thing, it's already run hot reload, Rust HTTP server, listening on localhost 3000. If I curl this, I get a pong back. And I can hop back into my Rust code and I can see okay, apologies for the massive thing that I'm about to show you. But essentially the one interesting line is this line right here, right? Pong from Rust crate. Pong from my Rust crate. And if I modify this, whoops. Pong, pong, pong. Watch it rebuild. My Rust server is listening again. I can curl again. I have pong, pong, pong. I have Python code calling for Rust code. And if I really want to do some wonky stuff, I can even have a stream going, right? That's the reason for the rest of this, all of these shenanigans, because you can do all of these things. So that's what the scope of things you can do. And you can imagine anything that is available in a Rust crate, from TLS parsing stuff to crypto primitives. Jack's the maintainer of Blake 3, which has been exposed through PyO3. Someone a few weeks ago talked about exposing some matrix analysis stuff. The folks over at Polars have been working on a pandas replacement in Rust. So there's a whole bunch of things, right? Basically, it gets you, hey, Python doesn't have types. It's hard to be confident sometimes about exactly the guarantees that you have and communicating to them to each other when you're working in Python source. It's a lot easier to do in Rust, so let's just do it in Rust. But now you have questions, right? So the first question that I would recommend you start asking is asking like what kind of API you want the users of your library to have to work with. If you use Rust objects, and the same, all of the rules of thumb, by the way, on these slides, I'm going to use Python for most of the examples on the slides. I'm going to use Python demo code, but the concepts are the same across all of them. And I can say that because I've written all of them, and I can actually bounce through some of the code, some of our production code to show you this. But if I use Rust objects, assumptions that you have when you write Python code kind of just go out the window, right? If you write a class in Python, a thing that you get when you write a class in Python is you get a constructor. You can go and say like, yeah, I want to build a list of like 1, 2, 3, 4, 5. If you do that in Python, sorry, if you do that in Rust, you now have to like define your Rust constructor and expose that to Python. If you want to be able to print an object using str, now actually I think I have demo code in here. I prepped a bunch of it, and I prepped it as a grab bag of kind of just like, here are all the things I can do. So let's go and do that. So I'm adding my Rust object back in. So that is this thing right here. So I have a Rust struct. It is annotated with PyClass. I have a bunch of methods on it that are annotated with Py methods. And kind of like along the similar lines, like we mentioned, Jack briefly alluded to this, that your foreign function signature has not a lot of strong intrinsic guarantees on what you pass into it, and that bindgen can help like reduce a lot of that boilerplate. That is the same across all of these libraries. There will be a lot of, shall I say, magic in the annotations for each one of these libraries that will kind of just do the thing that you want to do, with the caveat that you may still have to copy paste things more times depending on how many people have used the library and done the work of like reducing the amount of copy pasting that you have to do. But now that I have this, I can go and find my Python tab somewhere. It's in here somewhere. And I can do my Rust crate dot my Rust object dot my static method. Hopefully that returns something. Argument missing for my parameter text. I did something there. What did I do? It's supposed to take a text thing. Right, because my object, okay. So here, Python text. This one? Ooh, yes, this is coming out of Pyrite. So I am actually, so this is effectively VS Code. Pyrite is the default Python extension built in VS Code. There's also like, I will also note, just like how we were amazed that comments got propagated across the bindgen boundary, type annotations can get propagated across the Py03 boundary. They do not get propagated across the Ruby boundary because types are a lie in Ruby, and there are 4 different type systems in Ruby. And in Typescript, you do have types, but then you have to muck with TS configs, and it's a little painful. Python's actually impressively the easiest one to make work. So now I have Python text, and I'm gonna do this. Who has any idea what print X is going to do? It's gonna call stringify. So, ooh, did I? Because I'm still starting a Tokyo server, so it's never gonna get there. So now I'm gonna zoom in a little bit more, actually. So printing that gave me this jumble of thing, which is not really useful, right? Like if I want to debug anything, I don't know about you, my first resort is like printf. My first resort is like just go into the object, see what the heck is in it, and print it. And this like very basic assumption, right? Like I can do like d equals like asdef lorem ipsum, and like there's like no like true, there's no like single truth for the way you should print out a map. We all have different formats we want to print stuff out in sometimes, but like Python by default, like one of the reasons people use Python is that you can just like print stringified versions of random objects in Python and it'll just work. If you do that with Rust objects, now you have to like go and do it yourself. So you can go and add, you literally have to go and add like we're talking about magic. We're gonna see some magic. Sorry, can it be what? That's a good question. Let's find out. Yes. So the question was, can underscore str return a just string instead of a pi result of a string? And I just need to actually clone that. And I believe it will actually work. Yeah, there we go. Creative static method, Python text. So alluding to that point, right? Like everything in Python can fail. Any single like instruction, quote unquote, in Python is allowed to just say, nah, I'm gonna explode. And so like we can do like just pi result. Pi runtime warning. This is a runtime error. I think that may work if I import it, or if I wrap it in an actual error. There we go. Now I have a runtime error. But coming back, right? Like these are all things you now have to do by hand in Python in Rust, right? You have to implement your string representation. If you want to give more information about like if you want to do like the Python version of the debug traits, you have to implement repr. If you want to be able to use your object as a key and a dictionary and a map, you have to implement hash. If you want to do things with pickles, so Python has this like magic thing where you can say like, okay, I'm going to dump out all my variables to a file and then be able to load them back from a file. You use pickles, and you have to do magic for that. The sad thing is that like even if you don't want to do this, there are libraries in Python, including in the Python standard library, that will magically do this for you. And you will be very, very sad when you learn about this because you're going to find yourself like 5 layers down the rabbit hole and then be like, oh, it's pickling. And we didn't implement pickling on our very convoluted singleton object with thread pools, and now we're sad. Similarly, in other ecosystems, right? Like the same thing exists. In Node, if you want to support like JSON.stringify, which is basically like their version of prints for complex objects, you need to do this yourself. If you want to support destructuring, kind of like, so they have their own version of like destructuring as in Rust or unpacking whatever whatchamacallit. You have to do that. You have to think about like whether or not your objects are going to be compatible with that. Because if you just write a Rust object and you hand it back to a user in Node code, it's not going to support destructuring. It will maybe support JSON.stringify if you remember to implement the magic method that needs to exist on your Rust object for your Node user to be able to use it. But like it's not well documented. It's like kind of buried somewhere in documentation. Ruby objects, if you want it, and it's the same thing. The flip side of this, right? So that's one side of this decision that you can, whenever your users interact with your library, you hand back an object that your library created, and it's a Rust object, right? Like it's all the logic is your constructors in Rust, all the method calls are in Rust, and like they don't really get to interact with native facilities unless you build that yourself. The other way to do this is you say like, okay, you can just pass in a string from Python and we'll do, or like a random like class object, and we will do whatever we need to make it work. what will happen there is now you need to go and do all sorts of error handling. And what someone asked the question at the end of last talk, can you pass in an arbitrary value across the Rust C boundary? All of these languages, right? Like you can say like in Python, you can go and say like, oh, D is a dictionary. Well, D is now an integer. I'm going to print D. And then you can go like, hello world. And ignoring the runtime error, but like we saw D go from a dictionary to an integer to a string. This is a bizarre concept for those of us in Rust land, but Python is a different language. Python is a different world. This is a thing you are allowed to do in Python because there is a Py object that just encapsulates all of these things. And what happens if you decide that you're going to allow your users to pass in anything that they want is you have to start handling all of the cases yourself. You have to ask, oh, did my user pass in a false value? For some reason, false in Ruby is a singleton. It's not an actual Boolean. I don't ask questions. You got to ask, is it an integer? Is it a float? Is it a string? Is it an array? And then you have to do all of your own dispatch on top of that. There are Serde like things that you want to. There are Serde libraries in each of these ecosystems that'll allow you to basically say like, okay, if your thing looks like a JSON object, you can just use Serde and deserialize it into the thing. Unfortunately, if you've ever dealt with a Serde error and stared at it and wondered why it was failing, Serde errors are, they'll complain. They will not give you all the information you want sometimes. And at least for our cases, we were not happy with the errors that Serde did. We ended up handwriting a lot of this code, and it was painful. Even further, if you want to do anything with async, your life gets real complicated real fast. So the easy answer is to like just not deal with async stuff. Or if you do have to do with async stuff, be super lazy about it. Build a runtime and just tell the runtime like, hey, do the async thing and then like pretend to be sync. This is what we did in our Ruby code because we only have so many Ruby users, and fortunately, like they're running in like serverless environments, so like they don't really need to worry about concurrency too much. But like this is one way you can do it. And I believe rest. I meant to hop back to code at this point. However, if you do this, what did I want to do? I wanted to do this. I'm going to delete all of that code and go back to this. So I'm going to start my server via Tokyo. I'm going to delete something that was very, very important. So I'm back to running my server via Tokyo, exposing it from Rust to Python, and start server via Tokyo does literally this. It creates a runtime, and it says block on the implementation of my HTTP server. And it's just going to wait there. And now, I may regret this. I think I have to switch directories to be able to do this. Error while binding to address. Address already in use. Ah, okay. Let's just change port. I can leave a program just hanging there forever. This is going to be very sad when I press Control-C. And I'm just pressing Control-C over and over and over again, right? Because what's happening is that in this code, right, this is a blocking Python function call into Rust. And Rust is just saying, like, the Tokyo runtime is now in control of everything. So Python, which is by default listening for my Control-C, cannot do anything. Python is supposed to be listening for the Control-C handler, and now I'm kind of screwed because I have now shipped async code to my users, and they're like, hey, I can't stop your program. How do I get out of here? So the sad answer to this is that you have to tell them like, hey, sorry about that. Oh God. I'm gonna just minimize that real fast. Yep. Oh yeah. I'm going for kill dash 9. That was more processes than I expected to be running. That was possibly not the right process. We're gonna all right. Until morale improves. Well, fortunately, I can just do kill pain. And we will CD back into there. So now, if you're taking this approach, if you're saying that like, okay, my Python code is just going to call my Python code is just going to call my Rust code that's completely taken over everything and is now completely unresponsive, you now get to install your own signal handlers, right? Which is like the point of doing this is like to not have to do like I said you were going to have to do funky things. This is a funky thing you may find yourself having to do. But now, and this is going to fail because I'm in the wrong directory. Also, note the length of that command, right? Like, there's black magic involved. You will not fully understand everything. This is a thing you just kind of have to live with. But now, I can Control C, and voila! I can kill my Rust program. Yes, I return. Yes, I am now returning control to Python. There are better ways to do this. Okay, actually, first thing I should talk about. The reason that this goes haywire, right, is because every one of these ecosystems, if you're in the Python runtime, if you're in the Node runtime, if you're in the Ruby runtime, every one of these ecosystems has their own signal handlers that if you're running Python code, they install their own signal handlers in the process. Those signal handlers are the things that are supposed to be running. If you take over that signal handler manually, you may do bad things to the other Python code in there. The libraries themselves will kind of provide bridges. So again, or I alluded to this earlier, but if a library is more popular, there will be a richer ecosystem around it. People will have done more work so that you don't have to do it. You don't have to copy paste as much code. So if you're in Python, there's a Pyo3 async runtimes library that will just magically translate a Tokyo future into a Python future-shaped thing. Node will convert Tokyo futures into promises. Ruby, there is none. If you're in Ruby, you're sad. This is why we do our stuff in Ruby synchronously. The only people we know of that have actually done this are the folks at Temporal, which is like persistent workflow engine, and they like hand rolled their own thing. Yes, question. That is, yes, I will definitely take you up on that, or someone at Red Hat possibly. But to show you what this actually looks like, so there is another version of this down here. Start server via async IO, Pyo3, async runtimes, Tokyo, future into Pi. Again, a lot of incantations, just things are happening under here. But I will note, right, that start server impl is an async function. So what this means in Rust is that it's actually returning a future, right? There's this magic type annotation that shows up on async functions. And I can use future into Pi to just convert this into a Python object that in Python is a future. From Rust's perspective is just another Python object. And I'm not sure why this is complaining about it being unused. Oh, because I haven't exposed it. That's why. And now, if I go, or actually, I'm going to uncomment my control C handler. Remember, right? This was the thing that allowed me to actually control C my process. So I will also have to start server via async IO. I will now have to do this stuff. And I believe, yes, I also have to do async IO.run. Because async code in any language is painful. And now I can still curl. I will have to 3001. I can get pong, pong, pong. And I can control C. And it just worked under the hood. And the reason for this is because in the source code for this library, do I want to go and do that? That'll be fun. Let's do it. This may be risky. Source, it's a little wonky down here because there's a thing the library supports both Tokyo and async standard, but I believe cancelable. And deep under the hood of like what this like future into pi function, it goes down kind of like Jack went down the rabbit hole with like right and right and right and right and right. And if you go deep enough down the rabbit hole, you eventually end up here in this place where it's doing things with the Python GIL, global lock, and it's doing things with cancelable and says like, hey, if a cancel happens, kill the future. And that's how like this library is doing the async bridging. Control-C somehow works in Nappy in our node bridge. I'm actually not totally sure how, because when I went and looked at the code when I was prepping this talk, I got very confused by exactly how that was getting propagated. I just know it works because we've had users do it, and we do it ourselves, so like, in terms of how it works under the hood, this is another thing, right, that you have to start asking questions about like whether or not this is the model you actually want your users to deal with, and maybe you have to deal with it yourself. But essentially, what happened, the very high level hand wavy process of async and Tokyo, is that you have a loop, you have a bunch of tasks, you put futures into it, and you just say like we're gonna just loop over this queue. And we're going to do a thing, a work item on this queue. And they all of Python, Node, and Ruby have their own versions of this. How am I doing on time? 5 minutes? Perfect. That actually ended up being really close. I was concerned about my timing. And all of these bridges, in Python and Node, they exist for you. In Ruby, you kind of have to do it yourself. Also, again, I mentioned Ruby has 4 type systems. They also have like 3+ async systems because there was a different one every 5 years, kind of like front-end frameworks. Celebi. And in order of difficulty, or sorry, to wrap up the point on awaiting Rust futures in Python is just that you have to bridge these somehow. You should spend a little time, if you ever do this, thinking about and understanding how exactly it crosses the boundary, because it can and may or may not surprise you. But also, like a lot of things in these crates are magic. Sometimes you just roll with it. If it doesn't matter to the work you're doing, you got to pick and choose your battles on the things you actually spend time learning. So in order of difficulty, the kinds of call patterns you should think about. So imagine this is Python code calling Rust code. Calling a Rust function that takes no arguments. Simple. Calling a Rust function that takes arguments, it's a little annoying. Like maybe you have to do a conversion, you have to kind of worry about type safety a little, but it's not too hard. Awaiting a function, that's where you get back into like complex questions about like signal handlers and block on, and oh god, now I have to think about how event loops actually work, and why am I learning about event loops? All I want to do is call a function. If you want to give callbacks, your life gets painful. And if you want to do streaming across that boundary, now you have to start really doing some shenanigans. And I'm happy to talk about it, but I'm gonna avoid that until questions. And then here's the laundry list. Cross compiling still sucks in 2025. We have managed to solve propagating type annotations, but cross compiling is still very painful, right? Like I showed you this slide of like fix Windows thing, add more targets, right? Like this is still really hard, especially when you're bridging languages, because not only are you building Rust, you may or may not be building underlying C libraries for the thing that you're building in Rust, and you're building into Python, Node, or Ruby. Typescript, the ecosystems are smaller, right? Like of this set of Rust users, there are fewer people who write Python code in Rust There are fewer people who write Node code in Rust. There are even fewer people who write Ruby code in Rust. Documentation is just less abundant. Bugs will require going 3 or 4 levels deep. This is a bug I found my way to July of last year, because like things broke in the build ecosystem because CentOS 7, which is like, I don't know, 20 years old or something, like went end of life, and then our cross-compile toolchain broke. Reasons. TypeScript users still get confused about server versus client, because there are frameworks back that bridge this gap and do magic under the hood to move, like, split out code in a single TypeScript application between servers and clients. And if you have a library that only works on servers and not in browsers, things will just magically break, and then your users will ask you questions about, like, hey, how do I make your thing work? And then you have to explain to them, you kind of have to add magic strings in certain places. TLS semantics are their own balls of hair. Language versions, you have to start asking questions about, like, how far back do you support Python? Even though 3 is end of life, we still have users on it. Max ship with Ruby 2.6, which has been end of life for 3+ years now. And then crate versions, you now have to coordinate your Rust crate version with your Python package version, your npm package version, and your Ruby gems package version. We took the lazy way out of this. We just said we're going to pin them all to the same version, which means that if we want to patch fix one of them, we have to bump versions on all of them, but it works for us. And if you want to see the non-demo version, that is our repo. There is a lot of code in there. Please do give us a star. This is the shameless plug. We are very close to 3,000, and we're growing a community. So yeah, just take a look if there are if you want to see some wild, scary things. Questions or no time? Cool. Yeah.